Hello, multi-level modeling class. We are back within our example. Let's take a look at the extremely creative school data we'll be using today. So I'm setting some factors here. We will be predicting math achievement today. That's our dependent variable. Active time is considered time using a computer program. So we will be using a math learning platform. The students all will be using a math learning platform. And we hypothesize that the longer they use this learning platform, their math scores will be higher. We also hypothesize that the larger the class, the higher the impact of active time will be on math. That's because the software has all the students interacting with one another. Therefore, the more contributions, we think the better off that the student learning experience will be. So we anticipate a positive relationship of class size. Our clusters will be individual students nested within classrooms, and classrooms nested within schools. Classroom F is the variable I just made with classroom as a factor. So let's go ahead and take a look at the data. So I'm using grid arrange to take multiple ggplots and just put them together. Okay, and so initially what we see is that class size, as it increases, the relationship between math score decreases. This is counterintuitive to our hypothesis. We also see that as active learning increases, the more time students spend on the computers, the higher their math scores are. So that is the relationship we hypothesize. So that looks good. Here is a plot by classroom. So we see that each of the classroom slopes is positive, and that each of the classes see growth. Now let me turn that standard error off, which is the gray area, so we can look at these. Let's note some things here. It looks like the classes have different intercepts, right, where their 0 point of active learning is. And it looks like we do see some variation in slope. Here we see a blue class with a lower slope. But overall, the slopes seem relatively stable. The orange class here also seems to have a different slope here. It seems a little stronger. So it seems that we definitely have some variability at the intercept and maybe some variability in the slope as well, as they are not completely parallel. Now this line of code here is simply going to put school and classroom together because we are going to ignore so what this did was it takes every single school and the classroom within each school and makes a new factor. So school 1, class 1, school 2, class 1, etc., right? So we have unique class by school interactions because we are going to ignore the school variable for our first analysis and do a two-level model. Now I'm going to do grand mean centering. So to make interpretation easier, I'm going to mean center just globally. Across all classes, we're just going to take the mean and subtract it from everybody's score. And I'm going to do that for active time and class size. Now first and foremost, we should compute our intra-class correlation. And we have a high ICC, 0.74. So this is telling me that about 74% of the variation in math scores can be accounted for by the classroom cluster. So here's a summary of a multi-level model where I'm looking at active time, grand mean centered, interacted with class size. So we have the main effect over here on our summary. We have the main effect of active time, the main effect of class size, and then the interaction of the two. And so what are we seeing here? I also just have a random intercept for classroom based on this plot here. So it looks like we have a high variance for classroom. And let's break this down. So when active time is 0 or at its mean, and class size is at its mean. We have an expected math score of 42.96. A 1 unit increase of active time corresponds with an expected 14 unit increase in math score. So we have a pretty strong effect of active time. However, class size is showing us a negative effect. As class size increases by 1 unit, we expect the math score to go down by 1.86 units. Now we have an interaction effect here. Depending on what we're interested in, we could say a 1 unit increase in class size results in the slope of active time increasing by 0.3 units. Now this effect is non-significant, but it's marginally so. Let's take a look at another plot here. Okay. So to tie this plot back to the model, active time. The average slope here is 14 units-ish, maybe 15. And as class size increases, the slope of active time increases. Now that's counterintuitive to the main effect we see here. So what's going on? Let's add a random slope of active time to get a better idea. Now I failed to converge here, but I'm going to look at the model parameters anyway. We have a negative correlation between active time and the intercept. So this is telling me as the intercept goes up, the slope of active time decreases. So as a class's higher expected math score is at active learning equals 0, goes up, or active learning at its mean, the slope of active learning seems to be lower. And the lower the intercept, the higher the slope. And we can kind of see that down here with some of these. Now, this is what our fixed effects and random effects look like when we ignore the third level. This is not ideal, and this is not what we should do, but I'm using this to draw a comparison of how effects can change when we actually take clustering structures into account. So plotting 3 levels of data can get a little complicated, but here's my best attempt at it. So what do we have? The first plot on the left is the fixed slope of active time, okay? So this is just all the data. We're not breaking anything down by classroom. Here, in the second plot, we have the slope of each of the classrooms. And we can see that there is variation in the intercept and definitely some variation in the slopes. We see blue, orange, and definitely pink and magenta here are different as well. So we have variation in slopes and intercepts here, it appears, on active learning at the class level. Now here's what's really interesting. When I break it down, we have 3 schools. When I break it down by school, we see that not only is there a classroom effect, but there's a school level intercept difference here. And so it appears that these lower slopes are associated with the third school, the middle slopes are associated with the green school, and the red slopes are associated with the red school here. So we can't really just ignore this classroom cluster based on this visual assessment alone. So it is clear from the figure that active learning spans the whole range for both classrooms. But class size is confounded. Clearly, slopes vary as a function of the school. So let's take a look at what that looks like. These are centered based on the cluster means. But we can see that while class size may appear to have a powerful effect, a negative effect, we can see that we could just be measuring the effect of schools. It is completely confounded. Each school tends to just have very different class sizes. And so we can't be certain if the relationship between class size and active learning on math is truly an effect of class size, or if it's just a school level effect mixed with all the other variables associated with schools. School 1 just has different class sizes. School 1 tends to have larger class sizes and test scores, and compare that to school 2 or 3. And so this is a problem by ignoring nesting. Now, how big of a problem is it? I'm going to start by using that formula we saw in the lesson today to calculate an ICC for both levels of the model. So I fit the empty model and I extract, here's our residual, school level effect, classroom level effect. By taking those and breaking them down, I have an ICC of level 2 of the class of 0.31 and level 3 of 0.42. Now, so these two ICCs, the level 2 and level 3 ICC, sum to the ICC of the two-level model. So effectively, all we're doing with the three-level model is further partitioning these sum to the two-level model. We're just further partitioning the variance. And so what this is telling us, and this is how we would argue for a three-level model or not. We would test the ICC of the two-level model, and if we have the third level, we can test that. And it might turn out that class is doing all the work and schools don't do anything. But in our case, it shows that the school level effect is in fact stronger than the class level effect. So for us, it's going to be worth modeling. Now here in our small example with 3 schools, it's pretty obvious that, we can see that the school effect is large. But with many cluster, with a large school sample or a large level 3 cluster sample size, it might not be so obvious. So it's important to break this down in this way. So we can definitely justify using a third level model. So clearly the school level is important. Now, let's add the school level effect. Here I have a little guide for you, but I'll simply break it down. When we do a third level, we have to say we have an intercept for the school, and then we have an intercept for the school classroom combination. And so this is telling us that the school by classroom is a unique cluster as well. Now it's worth noting that that is simply just a product of our data because classroom scales from 1 to 10 within the first school, and then back down to 1 again. So this notation is simply telling us that the classrooms are unique within the schools. So read here, if classroom was completely unique, we would just have classroom here. But because it's not, we have to say schools are nested within, classrooms are nested within schools, right? Okay. So let's fit this model. Now this model failed to converge. This was the point in time I decided that convergence issues will be a major topic for our last day of class. We just can't get around it. We need to discuss what we should do. So I hate to say ignore this for now, but what I am going to do is use this trick called all fit. And all fit will refit this model with all of the different optimizers or estimation routines. You see these here. We have Bobby-Qua, Nelder-Mead, etc., etc. These are different means of estimating the model. That being said, we will discuss this in detail in the last class. So we will get past these convergence issues now. But for now, just know that I'm using this fancy trick in LME4 to extract a fitted model that works. I'm just choosing an optimization routine. So we'll discuss this later, but for now, just know this is the exact model I'm fitting, and we'll go from there later. So nothing else has changed. We just have our results table and no convergence warning because we have used a different routine that has successfully converged. Okay, so now we have a three-level model. We have active time and class size. What's interesting in noting here is that when we include the intercept at the school level, which is quite large, the effective class size goes down to 0. So active time stays significant here. As students spend more time in front of their computers working on the math program, their math scores go up by about 15 units. But by accounting for the school level variance, we see that the class size effect has diminished. It's now at 0, it's 0.95 p-value, not even close to significant. So clearly the school level was important in explaining the data. Let's take a look at the interaction. Aha, we do have a significant interaction. So this is telling us, even accounting for the school level variance, as class size goes up by 1 unit, the slope of active time goes down by 0.8. Now, this is relatively counterintuitive to what we saw in the plots. Let's take a look at that. It seems that as active learning goes up, each of the schools see an increase. But maybe if we take a random slope of active time into account, again, convergence problems, using my fancy fit method here. If we take active learning into account as a random effect, and we actually estimate the variance around that, we won't have the same issues with class size. And that's exactly what we see here. So class size is approaching non-significant, p-value of 0.07. And so now a very small decrease in the active time slope as class size increases. And that's because we've taken into account that active time varies as a function of the level 2 and level 3 clusters. This is the Simpsons paradox all over again. When we account for the fact that schools and classes simply varied in the amount of active time that they have, that's the intercepts here, and the slopes they have with active time. When we take that into account, we see that the relationship between class size decreases because class size varies as a function of the school. So, in essence, it seems that maybe there is some variance at both we can capture. We lost the interaction effect. It seems that once we account for the random slopes at level 2, we lost the effect. But why? That's because each classroom had a different class size. Adding variance to the slopes of active time. However, the model was explaining that variance via the fixed effects interaction, instead using active time and class time. When we treated active time as a random effect, that fixed effect went through the random slope. So let's make sure we need all of these random effects. Let's test them. So we realize that the differences in the relationship between active time and math via class size was actually just a function of the clusters. We see here very simply that the clusters have different mean values. So by taking those into effect and estimating the variance, the fixed effects are estimated without that confounding effect. So now I'm going to fit a model without active time at the school level. Okay, so we have some convergences here. I'll take the converged models, and we have highly significant effect. So I'm testing the level 3 at first, Active time is significant at level 3 as a random effect, so we will keep it at level 2 as well. So let's plot the random and fixed effects once more. Okay, so on the bottom I have the hat values. These are the predicted values of each student here. So in school 1, we see that in observed data above us. So in school 1, we see that the higher their intercept, the lower the intercept, the higher the slope. So that's a negative correlation between the intercept and slope. But their intercept is functionally different. School 1 just has higher math scores. School 2 has a little bit lower math scores. School 3 has the lowest. While their slopes are relatively similar across the schools, the class level slopes differ a lot. By not accounting for this, because the schools are confounded with class size, we would erroneously believe that class size actually has an effect on active learning, when in reality, it's just the school level differences that are leading to us believing that. And I have one more plot for us. All right. And so, once again, we see the need to use these higher order clusters to account for these differences in intercepts and slopes here as well at the classroom level to understand the relationship between active learning. Always keep in mind that these effects can be confounded by membership in higher order clusters. We could think we're measuring something when in fact we're just measuring something else. If that information is available to us, it's worthwhile to test and consider that we might just be confounding with another variable. So finally, I will look at the residuals of our final model, mod L37. The fitted values look perfectly fine. So we have a great residual here. I'm not very concerned. And we could even look at the normality here. So we'll say residuals. I will take the density and I will plot them. And we have relatively normally distributed residuals as well. So I hope this was helpful for you, or if not, maybe something you could at least look back on later as a guide to run a 3-level model, and just some of the things that we should consider in general. We could always be measuring something and thinking that that's all we're measuring, when in reality, it could just be a confounding factor of a different random effect or a cluster. Thank you very much for joining me for this presentation.